Alright everybody, let's look at another problem from section 4.8. We have a colony of bacteria that's increasing according to the law of uninhibited growth. If 10,000 bacteria are present initially and the number of bacteria doubles in 5 hours, how many bacteria will there be in 24 hours? How long is it until there are 500,000 bacteria? So one of the things that we notice is that this is uninhibited growth, which means we're going to use the equation n of t equals n naught e to the kt. And we know that the initial amount is 10,000, so we can already replace that. But we also know that it's going to double in 5 hours. So what this means is that n of 5 is going to be 2 n naught. So we know that in 5 years, the amount of bacteria is going to be double n naught. So this means we're going to have n naught's 10,000, so we're going to have 20,000 equals 10,000 e to the k times 5. So we know n naught's 10,000. This amount is doubling in the 5 years. What we want to do now is solve for k. So to do that, we're going to divide both sides by 10,000, giving us 2 equals e, and I'll write this as 5k. To solve this, I need to natural log both sides. And the 5k can now come down, and natural log of e is 1. And k is going to equal ln 2 divided by 5. So I want to show you two ways we can go ahead and write the exponential equation. For now, let's just use our calculator and approximate this. I get it to 0.13863. So this means our equation is n of t equals n naught, nope, not n naught, 10,000 e to the 0.13863 t. And in this case, the problem did not ask to write the function, but I really want to see the function written out. So I'm just going to go ahead and box this just as a reminder, like to write the final function out. And the reason why I think this is important is because I want you to use the proper function notation to finish answering the question. So there's two questions that we still have to answer. How many bacteria will there be in 24 hours? And then how long is it until there are 500,000 bacteria? So to do that first part, it's just going to be to find n of 24. So plug 24 in for t. I'm going to plug this in my calculator. Again, I'm just going to go ahead and plug this in all at once. So typing in the 10,000, e, and then everything up here is in the exponent. So I'm going to get approximately 2,857. Nope, that's not the right way to pronounce this. It's 278,579.95 bacteria. So that's how long it's going to take. That's how many hours. That's how many bacteria there's going to be in 24 hours. And then the next question is, how long is it until there are 500,000 bacteria? So in this case, we're going to find t. So the n of n of t is 500,000, and we want to solve for t. So we'll have 500,000 equals 10,000 e to the 0.13863 t. And to solve for t, divide both sides by 10,000. So we'll end up with 50 equaling e to the 0.13863 t, and ln'ing both sides. Allows the exponent to come down as a factor, and then ln of e is 1, so t is going to equal ln of 50 divided by 0.13863, and this is approximately 28.22 hours. Alright, so that's all the information. Let me just go ahead and box my final answers here. So we needed to find how long it took to get 500,000 bacteria, which was 28.22 hours. We also needed to find how many bacteria we had in 24 hours. So that's the 278,579. And I also would like you to box the function. So what I want to show you is another thing that you can do instead of getting your calculator at this point. So we had k equal ln 2 over 5. Alright, so I just wrote everything out, and what's happening is, in the way we did it before, I approximated ln 2 divided by 5 and plugged it in here. But what I wanted to show was that, what if we plugged in the exact answer? How can we play with it? Does our exponential function simplify a different way? And so the answer is yes. What I did was, I used the commutative property of multiplication, so I put the t in front, and I just made the 5 go under the t. So I have t over 5 times ln of 2, and now I have a factor times the natural log, which means the t over 5 can go to the exponent. And then, when you focus on the e to the ln base e of 2, those cancel and you get 2 to the t over 5. So it's that property of, like, b, or I think our author uses a to the log base a of x is equal to x. That's the property that I use from going from this step to this step. And so now the function just boils down to 10,000 times 2 to the t over 5. So you have another way to just rewrite your function. Either one's appropriate, and it's the reason why I also like this is that you can see some of our log properties play out. Alright, I'll see you in the next video.